3 value relation and 2 quadrant inside. So let's not worry about completely at this moment. You know that you will have a solution for so you can say that if the determinant of A is not equal to 0, then we say that A is non-singular. And if A is not singular, then A equals exists. So if A inverse exists, you can write this X as A equals times. Formally, that's all that you have to say. Formally, you have to say that if A is not singular, then you can find X. If A is singular, then you cannot find X. Okay? But you have to ask a question: how easy to get this A inverse? How do you find inverse of a matrix? Is it simple to find inverse of a matrix? How do we write the inverse of a matrix? Inverse of matrix. Supposing if you write this matrix as A11, A12, A13, A21, A22, A22, A31, suppose this is your matrix. Then you can define M23 as minor of A2. M23 as a minor of A2. What is a minor? Minor is determinant of, so A23 is this, so delete this column and this row. Whatever is remaining is the determinant of those quantities: A11, A12, A31, A4. This is called a minor of an element. Minor of a matrix element is defined as the determinant of the matrix deleting the row and column corresponding to the element. Then you can define what is called a cofactor. Cofactor of A to B is equal to -1 to the power the sum of row index plus column index into N. Cofactor of A to 3, which I will call it as C to 3. C to 3 is equal to -1 to the power 2 plus 3 into N. So you can write what is called a cofactor matrix. Cofactor matrix, you can take, now I have calculated cofactor of this. I can calculate cofactor of this, cofactor of this, cofactor of this, and so on. I can write a cofactor matrix. Okay? So cofactor matrix, I will call this as C as C11, C12, C12, C21, C22, C23, C31, C32, C32. This is a cofactor matrix. So in that, what I have calculated is the C23 here. This is C23. I can calculate like that every other element. And then I can write down A inverse. So A inverse is written as the transpose of this cofactor matrix divided by the determinant of A. The transpose of cofactor matrix divided by determinant of A. If I write it in the form of A inverse, an ij element of A inverse is equal to C ji, because Ct of ij, which means Cji, and then first that is Ct of ij divided by determinant of A, which is equal to C of ji divided by. Now you ask the question whether this is correct or why this should be correct. So let me ask a question whether what is A inverse into A. So let me take an ij element of A inverse A. This is equal to sum over K A inverse of Ik into A of Kj. Is that correct? A inverse of Ik into A of Kj. Now let me write down, this is what I want to verify whether this is correct or not. So let me write down A inverse of Ik as Cky divided by the determinant of A into Akj. Cki into Akj. Now what I have to show is that this is equal to delta ij. That's what I should get, right? Because this is identity. Identity of ij is delta ij. Okay. So I have to, of course, show you a couple of results before I demonstrate this. For example, if this is the cofactor, if this is the cofactor of 2, 3, so if I take cofactor of this, cofactor of this, cofactor of this, and cofactor of this, cofactor of this, you take any row or a column, and you have those cofactors. Okay, so you can define determinant of A as, for example, if I take A11, C11 plus A12, C12 plus A13, C1. If I take this row, the element multiplied by corresponding cofactor is given by the determinant. You can do that with any row or with any column. The determinant is, you take a row, find out their respective cofactors, the element multiplied by the cofactor and the sum of all such things in that row gives you the determinant. This kind of thing is called Laplace expansion. Any row or column. This is called Laplace expansion. So in that sense, I can write down immediately that I can immediately write down that sum over Cki into Aki, sum over K. What this will be equal to? It's determinant of A, because A is varying, I is fixed. it's like one is fixed and this is very fixed column. This is actually determinant of A. So note this. Note that this is equal to determinant of A. Okay. So what I am going to do is I am calling this as 1 over determinant of A into sum over K Cky into Akj.
That expansion in the second indices is in the first Laplace expansion.
Yeah, so it means what? It means suppose I have A13, A23, A33. So I take A13 to C33, C13 plus A23 to C23 plus A33 to C33. So the first element is changing, fixing the second element. That means I choose a column. That's it. So I can choose a column or a row. With respect to a column or a row, you can do this Laplace expansion. Okay, so in this, if I take I is equal to j, then that is equal to determinant of A. So that means this is 1. Determinant of A by determinant of A is 1. Now I have to argue if I is different from j, this will be 0. If I argue that, I can write this as delta I. So how to argue that one? Suppose I have this matrix A. Okay, so please follow this argument carefully. Suppose replace ith column of A by jth column. Ith column of A by jth column to get A prime. So A prime is a new matrix where I remove ith column, put jth column there, but jth column is also there. So I substitute jth column instead of ith column. What will you say about the determinant of A prime? 0, because if any two columns are same or any two rows are same, the determinant is 0. So determinant of A prime is 0. But if I take that particular column, what will happen to the cofactors? Will the cofactors of that column change whether I have the ith column or jth column? No, because that will anyway remove that column and that particular row. So cofactor matrix does not change. So if I ask this question that cofactor, that is I consider C Ki, so I will write down the determinant in this fashion. So determinant of A prime is equal to sum over K. So let me write at this moment C prime K I into A prime K I. We write it that way. Okay, A prime K I. But now C prime K I is same as C K I because by changing ith column to jth column, I am not going to change the K factor. So that means this is equal to sum over K C K I. And what is A prime Ki? Because the ith column is replaced with jth column, along that column I have only Akj, correct? So this is equal to Akj. Now this one is 0 if I is not equal to j. If I is not equal to j, the determinant is 0. So because of that, I can write down this one as delta I. This is the proof that this formula can be used to obtain A inverse.
Please repeat that after I try.
This argument?
Determinant I trying to write.
Yeah. So what I am saying is that if I replace, so let me say that I have an A here, and this is my ith column and this is my jth column. Okay, so jth column, let me write it like this. So I am going to replace ith column with the jth column. Now, this element is its cofactor, this element is cofactor, this element is cofactor. That is what this is. Correct? The determinant is 0. Now, this element's cofactor, this is my A prime. This element's cofactor is same as the cofactor of I or j cofactor will not change. So I am going to have C prime ki is same as Ck. Whereas A prime ki is same as Akj because I have replaced this column here. So jth column, kth row jth column, I am going to have A prime ki is Akj because jth column of A is kept as ith column of A to get A. And hence this is 0, so this quantity is 0 if I is not equal to 0. So this is the proof that A inverse can be obtained by this procedure. So we can write down A inverse like this. So if we have a small matrix, 3 by 3 matrix, you can easily do it. 4 by 4 matrix, not very pleasant, but maybe you can try. But if you have 5 by 5 matrix, 10 by 10 matrix, I do not know what is the biggest matrix that you have handled every time. I remember when I was working in Algebra, we had a problem where I had to invert 5000 by 5000 matrix, which is impossible if you want to do any kind of cofactors and things like that. So this is useful only for textbooks, solving some exercise problems in textbook. When it comes to applications, this is completely useless. This formula cannot be used.